Hi, it's Joshmi. In this session, we are going to learn how to implement JPEG inside MATLAB. I just created a roadmap, and here we go. This doggo, cute doggo, is our picture. The picture that we are going to discuss is in 500 to 500 image. As you see, it's actually not 500, 512, but if it's 500, there is a mechanism to do it easy, like 512, which is called padding. But thanks Lord, we don't need to do padding, so we just have it very fixed. If it's 1024, 2048, then we wouldn't need to do padding because we have to round it to look in this way to convert it to 8 to 8 blocks. Otherwise, it's not possible, and it would be so hard to convert to 8 to 8 blocks. Now for this 512, it's so easy. It's just 64 8 to 8 block, right? If we just multiply this 64 to 8 to 8, then you would get this 512 to 512. So yeah, we just use the IM show or image show inside MATLAB to, this line, forget about the other lines, just get these ones. To just import this image. Then later on, I just did this part and just, this one. So next we are going to convert our image to a grayscale, also called the luminance. We just separate the chrominance, which is that CB and CR. It's just 3 channels. We're gonna just put away 2 other channels and keep only Y, and this Y is called luminance. In a format of multiplication, like this one, as you see here, if you do this, you would catch the gray. And why we love gray? Because gray is so easy to do the compression. So we will just keep it, alright? And that's only for making the process easier. Otherwise, definitely the images you see every day in your life, in the internet, in your file or computer file managers, they're all inside. They're all YCbCr. It both has this luminance and chrominance, but we are going to discuss only the grayscale. That's only one channel. All right. And in the first part, I said 8 to 8 blocks. Why converting to 8 to 8, not 16 to 16 or 4 to 4? Look, this is the most optimized number the scientists figured out. And with this 8 to 8 block, for converting our signal in from spatial domain to the frequency domain, which we do it from here, like here, let me just do it. In here, it would be easier. It's just so hard to convert 512 to 512 immediately. Let's just do it step by step and make it easy. Alright, with this part, and later we are going to discuss quantization. But before going towards the quantization, let's just wait a little bit and discuss what we have talked about in here inside the MATLAB code. If you're in, we are going to dive deep. Alright. First of all, we just imported the picture, that's fine. Then afterward, I converted the picture from RGB to grayscale, and this is the number, and I just picked it up in the internet. It's in the internet, just search it out. So here we go. I just showed the image, and for converting it, I just picked up the size. And for example, if it's 1 block, then it would be 8 to 8, but here the grayscale is all the blocks. So that would be all the 512 blocks. Alright, okay, that was fast. I didn't expect that. Then later, this is, okay, keep this one. This is a constant. We are going to discuss why this constant and why we are keeping it here. Here, we are going to do the compression. When doing the compression, we like that lossy part. Why lossy part? Because that lossy part is where the real compression happens and we lose some signals. And how this happens, that's inside the quantization. So let's just keep it and go inside the compression. First of all, we just trying to convert this grayscale into some 8 to 8 blocks to make it easier. Then afterward, we're just going to do it one by one for the DCT to convert the signal from spatial domain to the time domain based on this code. And as you see in here, I just picked up the first row and first column of the signal to show the current block. Okay, just look at here. It's just the pixel. For example, if you pick up only one pixel, imagine it's only here. Okay, it's the first pixel, right? It's here, and I'm going to convert this one over here. This, if you sum all these pixels, that would make all this picture. But I'm just picking the first little part. So that has this value. That little 8 to 8 block has this value. And in pictures, what our eyes see is the brightness part, not the very like sharp parts. So this brightness has the lower frequency. Meanwhile, these sharp parts has the higher frequency. For example, these parts are sharp parts. And so when we are converting our signal from spatial domain to the frequency domain, we would see that we have a very high value, as you see over here, 1.1, I don't know, 420, whatever it is, in the top left part of the signal. We consider this part, this specific row 1, column 1, as the DC part of the signal. And that's where is the smoothness, the brightness. And that's where our eye is very, very clear to see it. So we're gonna just do some magic. We're gonna just do some quantization and quantization division, and somehow keeping this first value. Alright, whatever the value you see in here is multiplied to this value. I don't know, 10,000, I guess it is. Just multiply it to this one. Then later we are going to the quantization block. Okay, let's just go back to the roadmap. Look, in the quantization, we try to reduce the precision by dividing each coefficient by a standard value, making more of them 0 so they can be compressed better. So imagine we have many values over here, like higher frequency values. If I just, that's the 64 to 64 value, the last one, and the first one is 1 to 1. If we look at them, you can see there are very low values in here. And if I just divide them with these values, which the higher frequencies here and the lower frequencies here, these values, as you can see, is so huge, despite of here, which is so small. Why they are so small? Because we want this brightness, we want this lower frequency, because this is what our vision see. So we're gonna just compress them, and that's the first step of compression. So we're just gonna compress them with these values. So I'm gonna divide these frequency values that I achieved after DCT. As you can see, I got it over here, which gave me this value. I'm gonna divide it with these constants. So each value over here, for example, this value is 14,230 if you multiply it to this one, and if you divide it with this value, you would get this value. I didn't do the multiplication, so that's the value, whatever it is. So, but the important part is that the higher frequency is 0 now. And the cooler part is this round part. This round part is making the process lossy. What lossy means, look, other parts of the compression doesn't round the value. For example, you just divide 2 by, for example, 2.5 by 2, you get a value. And you multiply this 2.5 with 2, you get the same value as you had in the first part. But when you do the rounding, definitely you're going to lose some parts. That losing some parts is the real deal, is the real compression which is happening. The all other parts, as you see, is the process of compression, but none of them are really do the real compression. That's why the quantization is the core of the JPEG compression. All right, we did this one as well, very well. Zigzag, why we do zigzag? Okay, this is the format of zigzag. Before explaining, look, our signal is 8 to 8 block, right? We just convert this 8 to 8 in a zigzag format, as you see, one here, one here, one here, and here, to 164. It's like 1 to 8 to 164. Why we do this? We're just going to do run length encoding, and for doing this run lengths, we need our signal to be 1 to 64 to group them together. So we have to for RLE part section. But the question is why in this way? Well, why not just picking the first row and picking the second row, then third, four, five? No. Look, we try to keep the lower frequency in the beginning of this RLE to divide the DC and AC section. All right. So we're gonna just do this zigzag format. First, we just pick this one. Then the most closest to this lower frequency is this one. Most probably these values, as you see first, 2 second, these blocks as inside the zigzag are not zero. And wherever you go inside the higher frequency, you see zero. So, and then for grouping them, it would be so easy to group many zeros. We are not going to give the Huffman coding, which is the step after, okay, go away, a step after RLE. We are not going to give them 64 values, which around 60 of them are just zeros. We're just going to group these 60 values and say, okay, 60 of them are zero. It's not going to do 60 calculation. It's just going to do one calculation for these small zeros. Actually, big zeros, many zeros we have over here, based on the compression or actually quantization. So yeah, we got what the zigzag is as well. Then we have RLE. Okay, how I did the zigzag. Look, before going on, look, zigzag map is a function, and yeah, I just defined the function at the end of the code, and this is exactly this picture. This is exactly this picture. That's how the zigzag format is done. I didn't do this code. I just picked it up in the open source in the internet. And if you want, I can just share this one as well. Just comment me in the comment section and I will email you. So we have the zigzag map and we pick these 8 to 8 blocks and convert it to 64. Here you go, it's just 1 to 64. Let me see, it is, yeah, flat vector is 1 to 64. As you can see here as well, yeah, 1 to 64. Alright, let's go next step, RL encoding. This one, look, we are keeping the first value of this zigzag, which is 89. And we consider this the DC component. As you can see, I wrote it over here. And we are going to flat vector the rest of the values till the end. It would be 0 until the end of the code as the AC values. We just separate them because for doing the compression, we do different compression for DC. We just don't do it as we do it for the AC. So we don't group them. We just group the ACs. Okay, that would be 63. Yeah, as you can see, 63 values from -1 to until the end. Alright, this JPEG RLE is again another function which I didn't code. It just groups them together. How it groups them? It just groups them like this. Yeah. Just makes them like 15 0, 15 0, 15. That would be around 45 0 and other values. So, sorry. So here we go. Alright, then here we go. We have the for loop which makes these output as you see in here. And I just picked up one of them and showed it over here. That would be 64 definitely. So we are going to store all these values for Huffman. Then here we go, we just going to unique sims. As you see, it's just keeping the symbols, unique symbols. Like in here, the unique ones is 1, -1, 15, 0, and 0, 0. We are not going to pick all these three 50 0 50 0 50 0. What is unique between them? 50 0. So we're gonna just pick all the in here is just taking all the symbols. We have the block symbols which only 8 to 8, and all the symbols is for 500 to 500. Then we are going to count these unit symbols, like considering, or better to say, considering a frequency to these unique symbols. For example, in here I have, let's just make it so easy, it's just being so weird. Okay, imagine I have, okay, this is text, I have A, B, C. What Huffman does, in here Huffman sees that, okay, A is repeated 3 times, and B is 1 time, and C is 1 time. In here we have 3 symbol, or this 1 message and 3 symbol. In here this 3 symbol has the most occurrence. The more the occurrence it is, the more probability it would have, and the less bit we would give to it, because the less the value is occurring, the more valuable it is for us. All right, that's the code for it. So for example, in here, if we say the frequencies, maybe, okay, the frequencies is, for example, 10 hertz. So if I want to assume values in here, I would just give 6 values to the red, 2 values to the B, and 2 values to the C. And if we try to take its probability, that would be, the prop would be A would have the probability of 0.6. We are just dividing it to the whole frequency. And B would be, B would be 0.2, and C would be 0.2. Why? I'm just considering the probability like this because the sum of the probability must be 1. So as you sum these ones, that would be 1. And when we are encoding, we are just giving bits. And how is this encoding is done? That's whole another video. And I just put a simple format over here how the encoding is done. But I just wanted you to know that we are going to give less bit to the most probability of the signal and the symbol, and the least probability of the signals will get the most bits. All right, so we would just get a bit stream in the output, and that's the probability, the frequency, and the sum of all frequency. That's obvious, I just said it in here. And we are going to make a dictionary for the Huffman encoding. So we're just gonna take the unique symbols, the probability, and here we are going to do the encoding. So at the end of the line, we would have some beta streams. And beta streams are not our, okay, I just saw something cool. What was that? Here we go. Look, the first one is being repeated many times. For example, I don't know, whatever it is. And we are just assuming very small bits to it. It's just 3 bits. But the lower ones, I don't know the exact values, but the lower ones are being repeated less. So as you can see, we are assuming or considering, better to say, higher bits to these ones to make it more valuable for the receiver to get it. We transmit and the receiver get it. Okay, we are just doing the coding, then afterward decoding to get the message. So yes, as I said, we are going to do the decoding. And why we are doing the decoding? We did all this compression to do this encoding. Why the hell now we have to do the decoding? You would ask yourself now. Look, we want the message. What we did over here would give a bit stream in the output, just some values, some numbers, like here, just some numbers. 1 0 0 1 1 1. That many values, and it's not being. So we are going to do the decoding to get the message output. But what's the difference over here? Instead of giving, for example, 3 bits to A, 3 bits to B, 3 bits to C, we are going to give 1 bit to A, 3 bits to B, and 3 bits to C. How this compression works? Now this A doesn't have 3 bits. Normally, if we don't do Huffman, all of them has the same bit value, 3, 3, 3, 3, 3, 3, whatever it is. But now this value is 1 bit and this value is 3 bit. That's 2 bit less, and that's where Huffman is the king. So we are going to do the decoding and reshape it just to make it normal look like, it's not looking normal in here. We have to do the reshaping to make it look like Paris in here. Then we are going to give it to the where is the RLE here? We are going to give it to the RLE. Then it again does the inverse RLE here. Okay, it just does the inverse RLE. It means it just ungrouped them, not grouped. It ungrouped them to, then after it gives the ungrouped ones to the inverse zigzag. The ungrouped one is 1 multiplied to 64. We don't like 1.64. We want 8 to 8 block. Then we are going to multiply that quantization constant value that we did the division on the signals, and eventually convert our signal from the frequency domain to the spatial domain by the IDCT, or discrete cosine transform. Inverse discrete cosine transform. Yeah, we did this line, and here block inverse zigzag, and this is the function that we defined. Then the quantization is now 8 to 8 because we did the inverse zigzag, and we are going to multiply it to the same constant we had it because we are just doing the dequantization. Then converting to the spatial domain and reconstruct the signal. It's just reconstructing it to 500 to 512. Here 500 to 512. Then you are showing it and putting a title. This is the final output. If you see this picture, the quality, as you see, is much different than the first one. Okay, not this one, this one. You see? That's barely what our eye can see. It's important that we are keeping the brightness. Because if we did the compression to the first top left matrix values, we would have an output which is like black. But now you see the brightness is fine, but the sharp parts is less smooth as the first one, right? So here we go. That's the end of the Huffman, or better to say JPEG compression. We did all of this. Thank you for following me.